All right, we are continuing with our studies of the hydrogen atom. We wrote the wave function. As a radial function, and U and L we showed was proportional to here alpha is 12 plus 1 and n is n minus L minus 1. L is the orbital angular momentum quantum number, n is the principal quantum number, and L can take the values for fixed n, well, integer values from 0, 1 to n minus 1. And then we showed the representation of the associated Laguerre polynomial in the complex plane, and then we obtained the generating function of these Laguerre polynomials, namely generating function we obtained using the integral representation of the Laguerre associated Laguerre polynomials as this is n equals 0 to infinity u to the n L alpha n of z. Okay, we have this closed expression for this infinite series. And I again remind you, in some books and papers, you will find this expression, un L alpha n over n factorial. So these are related to each other with an n factorial. So one has to be careful from which definition one is starting. We shall use this one. So I'm erasing that. And this lecture's first part will be using the generating function to obtain various relations between these associated Laguerre polynomials. So I'm erasing this, and I will write this to the top. G alpha u z u n and I'm erasing this part. All right. During the computation, I will drop these indices, upper index alpha on the generating function and the associated Laguerre polynomial, just for the economy of writing, but at the end, I will put them back in. So I will simply write G as and L, and then I will write them. So how do we obtain relations between different polynomials using the generating function? Let us differentiate with respect to z, delta zg, by which I mean this is equal to 1 over 1 minus u alpha plus 1 times e to the minus zu over 1 minus u times the derivative of inside. So this is minus u over 1 minus u. We multiply out 1 minus u delta zg. This is just g That's equal to minus UG. So that's our relation 1. I will call A. 2. This time, let us differentiate with respect to U. I'm differentiating this. So it is minus alpha plus 1, 1 minus U, alpha plus 2, and the derivative of inside, minus 1. Derivative of 1 minus U with respect to U, that's minus 1, times e to the minus ZU, 1 minus U, plus 1 minus U, alpha plus 1, e to the minus ZU over 1 minus U, times d by du minus U over 1 minus U. So we have to take the derivative here. By the way, let's do this part. This is minus minus plus, alpha plus 1 times G over 1 minus U, plus this is G times d by du minus Z here, d by du, U over 1 minus U. This is equal to 1 over 1 minus U minus U, 1 minus U square times the derivative of inside. That's equal to 1 over 1 minus U square, 1 minus U plus U. So it's 1 minus U square. So this is equal to alpha plus 1 G over 1 minus U minus Z times G times 1 over 1 minus U square. Or if I multiply it by 1 minus U square, 1 minus U square delta UG, that's equal to alpha plus 1, 1 minus UG minus ZG. So this is B. Let me write A and B together. I'm erasing the derivation. I will just write the results now. I'm writing this upstairs. 1 minus U delta ZG. That's equal to minus UG. That's our relation A. And I will simply copy B to here. Remember, this came from delta ZG. The second one comes from d by du. So let's copy it. 1 minus U square delta UG equals alpha plus 1, 1 minus UG minus ZG. And that's our relation B. I'm erasing this one. So the first relation comes from taking the derivative with respect to z of the generating function. The second one comes from taking the derivative with respect to u. Of course, G involves all these associated Laguerre polynomials, which will translate into relations between various Laguerre polynomials and their derivatives. And we can also combine the two derivatives, a and b. So let me just write a, b together. To do that, for example, we have a combination here, u over 1 minus u. So let us divide this thing by 1 minus u. So 1 minus u du g, that's equal, this goes away, alpha plus 1 g minus z 1 over 1 minus u g. I simply divided this b by, this is simply b over 1 minus u. Let us write 1 over 1 minus u as follows. This is 1 minus u plus u over 1 minus u. This is 1 plus u over 1 minus u. So we put that here. This is minus z g 1 plus u over 1 minus u. That's equal to minus z g minus z gu over 1 minus u. And if you look at a, minus ug over 1 minus u is simply d by dz of g. So if I combine all of these, this is dz(g). So this gives finally 1 minus u delta ug, that's equal to alpha plus 1 g minus zg plus z delta zg, or this one is alpha plus 1 minus zg. So I will simply write this thing to the top. AB gives a relation between the derivative with respect to u and with respect to z. 1 minus u delta ug, that's equal to alpha plus 1 minus zg plus z delta zg. I am erasing the rest. This is the derivation, that's the result. So we have three results, A, B, and the combination A, B. So I will erase now the calculation A, B. Now, G, as we mentioned, I hope this is not... Now, what do we have here before we try to dig out the relations implied by AB and AB on the associated Laguerre polynomials? So let us write here all of them, whatever happens. G is UN, L, N. Remember, alpha indices are suppressed just for the economy of writing. At the very end, I will put them back in. All right. Then let us see what multiplies G. I have a U. So UG is equal to UN plus 1 Ln. Any other power? No. Then we have the derivatives of G. So delta UG, the derivative with respect to U, that's equal to, I'm taking the derivative of that, N UN minus 1 Ln. Then this derivative is multiplied by 1 minus U square. So it's multiplied by 1, multiplied by U, and multiplied by U square. So if it's multiplied 1, it is that. Then we have U delta UG. So that's N U to the N Ln. Then we have U square delta UG. That's equal to N UN plus 1 Ln. So that's about it with G and DUG. Next we have d by dzg. The derivative with respect to z, G. The part that depends on z is the associated Laguerre, so it is the derivative with respect to z of the Laguerre. Then we have U delta zg. All right. Now we can read off the relations between different Laguerres like this. I am looking for the coefficients multiplying UN. So I'm using A now. I'm here. Delta ZG, I'm extracting the coefficient of UN. So that's Ln prime minus U. But this has UN plus 1. I am looking for the coefficient of UN. So reduce this thing by 1, UN. You are reducing this n by 1 to n minus 1. Minus L prime n minus 1 equals minus UG. UG is here. Again, reduce n by 1 to get UN. So that's Ln minus 1. Minus Ln minus 1. Now we can put the alphas back in. All right, this is the first set of recurrence relations. By the way, what are we doing? We are trying to get the recurrence relations of L alpha n's. B. First, it is, if you open it up, this is 1 minus 2u plus u square. So 1 gives me that n, un. To get to un, I must increase n by 1. So this is n plus 1, ln plus 1. So n plus 1 times ln plus 1. That's the first term. Second, minus 2u. Here. Minus 2u. Minus, this is already un, so minus 2n ln. Minus 2n ln. Plus u square, namely when we open it up, plus u square. this is now n plus 1. So to get to un, I must use n minus 1. N minus 1 plus 1 is n. So this is n minus 1 plus n minus 1 ln minus 1. That will be equal to equals alpha plus 1 g minus zg. So alpha plus 1 minus z g. G already comes with un, so it is simply ln. Then we have this one, alpha plus 1 minus ug. So it is plus alpha plus 1 minus ug. ug is here. Reduce n by 1. This is ln minus 1. So I would rather, for reasons that will be clear later on, put zln to the left. So zln to the left. Then this becomes 2n plus alpha plus 1 ln. For reasons that will be clear later on, I want to take this zln to the left and leave it alone there. Zln is 2n ln plus alpha plus 1 ln. So we are done with the ln's. Then minus n plus 1 ln plus 1 and minus n minus 1 plus alpha plus 1 ln minus 1. That's it. This is just n plus alpha. Let me write it here again. This was the calculation. Let me just copy the result. Okay, I'm erasing this part and copy the result here. ZLN, that's equal to 2n plus alpha plus 1 ln minus n plus 1 ln plus 1 minus n plus alpha ln minus 1. So this goes. All right, we are at the combination AB. DUG. So again, we are looking at the coefficients of U to the n. Just DUG. So it is n plus 1 and then minus u du. It is this, so it is minus n ln. That's equal to alpha plus 1 minus z ln. dz is un ln prime. Z, it is simply un plus z ln prime. Or ln plus 1 times n plus 1, I can put the index now, equals, putting it to the other side, n plus alpha plus 1 minus z l alpha n plus z l alpha n prime of z. So we obtained three relations. Of course, one can generate many more, but for the purposes of these lectures, this is enough. Incidentally, we can use this nice recursion relation because Ln plus 1 is related to the derivative and the function itself of one lower. So you can generate the higher associated Laguerre polynomials just using that. So let us do one or two simple ones. I'm erasing because we wrote the relations. We know that L alpha n equals 0 z is equal to 1. Now let us get L alpha 1 of z using this recursion relation. So to get to L1, we can put n equals 0, 1 times L1. So this is 1. So alpha plus 2 equals alpha plus 2. No, we put n equals 0. Let me just write it here so that we don't get confused. Alpha n equals 0, alpha plus 1 minus z times L alpha 0, but L alpha 0 is 1, times 1, times z times the derivative, but the derivative of this thing is 0. So z times 0, the derivative of that. So that's 0. So we have alpha plus 1 minus z. That's the first one. Let's do one more and stop. To get to L2, and we can put here n equals 1. So this is L2, 2 times L2, n equals 1. 2 times L alpha 2z, that's equal to, we put 1. So that's alpha plus 2 minus z, alpha plus 2 minus z. L1, what L1 is alpha plus 1 minus z plus z times the derivative of the first one, that's minus 1, plus z times minus 1. And so if you multiply alpha 2 and alpha 1, so it is alpha plus 1, alpha plus 2. Then it's the constant term, then the linear terms in z. So minus z, alpha plus 2, then alpha plus 1, and this is also 1. All right. Then plus z here minus z square minus z plus z square. This is also 2, alpha plus 2. So altogether this is 2 times alpha plus 2. And I am dividing by 2. So L alpha 2z is equal to 1/2 alpha plus 1 alpha plus 2 minus alpha plus 2 times z and plus z square over 2. So it checks with what we have found before. All right. In this part of the lecture, I will discuss the orthogonality properties. Orthogonality of Now, the associated Laguerre polynomial satisfied this equation. And perhaps the easiest way to discuss the orthogonalities is looking at the Sturm-Liouville character of this equation. Sturm-Liouville equation reads some dpd. P is a function of x plus q. Q is a function of x acting on y is equal to minus lambda w y. By the way, we know that the solutions of this thing that do not explode infinity are the associated Laguerre polynomials that we studied. Now we are looking at the orthogonality properties of these polynomials and what is the Sturm-Liouville form of this equation. And so we will try to form correspondence. By the way, this is just an application and I'm not giving the general theory of Sturm-Liouville's. So this reads P y double, second derivative, plus P prime y prime plus Q y, that's equal to minus lambda w y. Remember, P is a function of x, Q is a function of x, and w is a function of x in general. So we will try to find what kind of Sturm-Liouville equation this one is. First, this obviously is the eigenvalue n, and q is equal to 0. So we have q is equal to 0. And if we compare p and p prime, we cannot really immediately identify x with p. It's just we can, because there may be common factors, the best thing is to look at this divided by that is just the p prime divided by p. So p prime, I am trying to find the p, q, and w that are appropriate for this associated Laguerre differential equation. So p prime over p, which is dp dx divided by p, that's equal to alpha plus 1 minus x divided by x. This is alpha plus 1 over x minus 1. So multiplying both sides by x, we obtain dp over p. That's equal to alpha plus 1 over x dx minus 1 over x. And this integrates very easily. Log p equals log x to the alpha plus 1 plus dx, and there's another dx here, just dx, minus x plus constant, and let me write that constant as log c. And if I exponentiate, p of x is c times x to the alpha plus 1 times e to the minus x. So this is p of x. So I am writing this equation now. C times x to the alpha plus 1 e to the minus x y double plus the derivative of p. So it is constant is multiplying. So it is alpha plus 1 times x to the alpha times e to the minus x minus x to the alpha plus 1 e to the minus x times y prime is equal to minus lambda w y. I take this to constant times x to the alpha e to the minus x parenthesis. This gives me x alpha is out, so x is left, x y double plus alpha plus 1 minus x y prime. Now lambda is n, so it is plus n y, and I have divided by w. So we have associated the integer n with this lambda, the eigenvalue, and we choose the weight function. That's why I call it wx over constant as x to the alpha e to the minus x. So if we do that, this is 1 because this is 1. We are simply left by this associated Laguerre differential equation. Now, however, Sturm-Liouville demands a boundary condition to be satisfied as well. And let me see where I can erase. All right, I'm erasing this part. It demands that BC must be satisfied. P of x times yn prime minus ym, namely function and derivative belonging to different eigenvalues, yn prime. And the limits should be such that AB, that should be 0. Now, P of x is C times x to the alpha plus 1 e to the minus x. C does not play a role here. We can just take it to be 1, the constant. Well, what should we choose for A and B? If we choose A to be 0, A equals 0, this is 1. X goes to x alpha plus 1 goes to 0. But how about here? These, for example, yn goes as a0n plus a1n x. And the last one is a n x to the n. So if you take the derivative and then set x equal to 0, only the a1n remains. Or if you set the x equals 0, only this term remains. So this thing goes to a constant in the 0 limit, and that part goes to 0. So a equals 0 is okay. It goes to 0 because of that, and this doesn't cause a problem. And what about b? If we choose b to be infinity, b positive infinity, then e to the minus x dies, and this is a polynomial, so it has the highest power x to the n, and it will kill, the exponential will kill any power. So a, b are from 0 to infinity. So if we set this is equal to 0 and this is equal to infinity, this is satisfied. In that case, we know from the Sturm-Liouville theory that there's only one more condition I should state. Wx should not change sign between the limits a and b. So Wx is simply x to the alpha e to the minus x. This does not change sign between 0 and infinity. So therefore we can say 0 to infinity dx, Wx, which is just x alpha e to the minus x, x to the alpha e to the minus x, L alpha n x, L alpha n x. This is proportional to delta n. The question is, okay, Sturm-Liouville theory says that with this weight function and with these limits, associated Laguerre polynomials of any arbitrary integer n and positive integer n and m are orthogonal. The question is, what is it equal to? So we can say that this is delta n and some integral jn. So now we will find jn. They are orthogonal with this weight function. So we will try to get the in some sense the normalization integral of the associated Laguerre polynomials. Okay, I am erasing this. To find this value, we will again use the generating function. So consider the integral I equals from 0 to infinity dx x to the alpha e to the minus x g of g alpha ux g alpha hx. Okay. So we will take this integral using the generating function. And let us remember what the generating function is. G alpha ux is equal to un L alpha n, which is 1 over one minus u alpha plus 1 e to the minus x u over 1 minus u. Okay, so this is equal to sum over n and m un hm 0 to infinity dx x to the alpha e to the minus x L alpha n x L alpha mx, which we know is proportional to the delta function. But let's leave it for the time being like that. Let's call it J and M. And now this is equal to, we put the compact form of the generating functions, 1 over 1 minus u alpha plus 1, 1 minus h alpha plus 1, 0 to infinity dx, I'm erasing this part, x to the alpha e to the minus x, simply that e to the minus x 1 plus this 1 comes for this. Now I will write one with gux, the other one with xhx. Minus x plus u over 1 minus u plus h over 1 minus h. And we will take this integral. So let's evaluate the term in the parentheses. So it is 1 minus u, 1 minus h, plus u minus uh, plus h minus uh, divided by 1 minus u, 1 minus h, equals, let's multiply 1 minus u minus h plus plus u minus plus h minus divided by 1 minus u, 1 minus h, equals, u cancels, h cancels, one of the UH's cancel. So this is equal to 1 minus UH over 1 minus U, 1 minus H. Let us call this for short A. So our integral now reads 1 minus U, 1 minus H, altogether alpha plus 1, 0 to infinity dx x to the alpha e to the minus ax. The change of variable is obvious. S is equal to ax, x equals s over a, and so that's equal to 1 minus u, 1 minus h, alpha plus 1, 1 over a alpha, another one from here, alpha plus 1 times ds s to the alpha e to the minus s from 0 to infinity. This is a well-known integral. I can write S of alpha like this, S of alpha plus 1 minus 1. And this is simply gamma function of alpha plus 1. But our alpha in the hydrogen problem is 12 plus 1, which is integer. Therefore, this is equal to alpha factorial. All right. And A is this term. It is in the denominator. So in the denominator, we have 1 minus UH to the alpha plus 1. And these are in the denominator with power alpha plus 1. And they cancel the whole thing. So the result, this was just the evaluation of the parenthesis I'm erasing. The result is equal to 1 over 1 minus UH alpha plus 1 times alpha factorial. Because alpha is integer in our case. This we will compare with UN, HM, J, and M. Now we can expand this thing. This is alpha factorial times sum over P alpha plus 1 plus P minus 1 P U to the P H to the P. This we shall compare with this result. Sum over N and M UN, HM, J, and M. Let me, this is alpha plus P factorial divided by P factorial times alpha factorial, which cancels that. So that's equal to sum over P UH to the P times alpha plus P factorial divided by P factorial. Now, when we compare, what do we see? Here, only the powers of U and H equal powers appear. Here, there is N and M. So, they have to be equal. That means the J integral is diagonal in N and M. That we know from the Sturm-Liouville already, but it comes out in the integral anyway. So I can erase, this was part of the computation. I'm erasing. We can read the value of J and M here. J and M equals delta NM, because the powers of U and H must be the same. And here we take P equals N. So it is alpha plus N factorial divided by N factorial, which is delta NM, which is just this integral 0 to infinity dx x to the alpha e to the minus x L alpha n L alpha m. Okay, it is orthogonal, and when the indices are equal, it has this value. All right, so we have computed the orthogonality properties of the associated Laguerre polynomials. They are orthogonal with this weight function, and for the equal values of indexes, this is the value of the integral. Now, I will erase the blackboard, and then we shall consider the normalization of the hydrogen wave function, because that was our aim to begin with. All right. In this last part of the lecture, we shall discuss the normalization of the hydrogen atom wave functions. We discussed the normalization of the associated Laguerre polynomials, but of course we are interested mainly in the normalization of the hydrogen wave functions. So, by the way, this is the recurrence relation that we found in the first part of the lecture in B. Remember, that was derived from taking the derivative of the G generating function with respect to U, and it gave this relation. We shall use this one, since it's a long one and one doesn't remember. I wrote it up. All right, coming back to the wave function, we have psi n l m that's equal to r n l y l m r. This is just the angular part, and r n l is n, the normalization. Perhaps it will depend on n and l. N is the principal quantum number, times r to the l. U, which was r times, small r times this wave function, was r to the l plus 1. So this is just r l. E to the minus r over n times l to l plus 1 and minus l minus 1 to r over n. And the integral should be 1. So from 0 to infinity dr r square. So we want this integral n square to be found. This coming from the spherical integration, integration in the spherical coordinates, then r to the 2l. I'm writing this 0 infinity dr r square should be 1. R square r to l e to the minus 2r over n, l to l plus 1, which we call alpha. N is n minus l minus 1 to r over n square. So this is r 12 plus 2. This result should be 1. And let us change the variable. Let's say x equals 2r over n, r equals n over 2x. So this is equal to n square. 12 plus 2 and 1, n over 2, 12 plus 3, times 0 to infinity dx x to the. This is alpha plus 1. Alpha is 12 plus 1. So this is x alpha plus 1 e to the minus x l alpha n x square. Now, this is, however, not the integral we found for the in the Sturm-Liouville problem for the Laguerre polynomials, where we had x to the alpha. Here we have x to the alpha plus 1. Now, how to take that integral? Now we will use this recursion relation, because we will write this thing as n square, n over 2, 12 plus 3, 0 to infinity dx x to the alpha e to the minus x. One is alpha n x, and the other one will be x alpha n x. So I will use for x ln, I will use from this recursion relation z replaced by x. Now, so if you replace this thing with all these things, n plus 1 integral and n minus 1 integral will give 0, because n plus 1 is not equal to n, n minus 1 is not equal to n. Only this one will contribute. So let us write this. This is nl square, n over 2 12 plus 3. Only this term will contribute this integral. So I have this factor 2n plus alpha plus 1. And I have an L alpha n integral, and we just took it. That was alpha plus n factorial divided by n factorial. That's it. This should be equal to 1. Let us compute what this is. This is 2n minus 2l minus 2. Because n is the principal quantum number minus the orbital minus 1, plus 2l plus 1 plus 1. That's equal to minus 2 plus 2. So these cancel. 12 cancels. So this is simply 2n. And what is this? This is n minus l minus 1. That's n. Plus 12 plus 1. That is equal to n, one's cancelled, plus l. All right, so this is equal to nl square, n over 2, 2l plus 3, 2n, and n plus l factorial divided by n minus l minus 1 factorial. And this result must be equal to 1, so that we can now write n and l. N and l is equal to 1 over square root of n over 2, 12 plus 3, 2n, n plus l factorial over n minus l minus 1 factorial. So this is the normalization constant for the hydrogen wave function. I'm erasing the computation. All right. We normalize the hydrogen wave function. Therefore, again, let me write. We mentioned psi NLM is a radial function, which is this. This is the associated Laguerre polynomial. NL is given like that. And that's it. Let us write one or two simple wave functions. For example, R 1, 0. N equals 1, principal quantum number 1. So it is 1 over root, let's compute, n equals 1. So L equals 0. So it is 1 over 2 to the cube. 2 cubed. N is 1, so it is 2 and then n plus L. This L is 0, 1 plus 0 factorial is 1 factorial. Here it is 0, 1 minus 1, 0 factorial is 1, so this whole thing is 1, times R is 0, n is 1, e to the minus R, L 1, L is 0, and this is 0. So this is just 1. 2. So this is simply 2 e to the minus R. This is R1, 0. Let us compute R2, 0. Namely, n equals 2, L equals 0. Two divided by 2, that's 1. So this is 1. 2n, I have 4. Then L equals 0, n equals 2. 2 factorial is 2. 2 minus 0 minus 1, 1. 1 factorial is 1. So I have only 2, another 2 here. Then this R to the L, L is 0, e to the minus R over 2. Then L alpha, n is 2, L alpha 1 of 2R over n, and n is 2. So this is alpha plus 1 minus z, which is R here, and alpha 12 plus 1, L equals 0, it is simply 1. So it is 2 minus R. So R2, 0 is equal to 1 over root 8 e to the minus R over 2, 2 minus R. Let me write it here. R2, 0 is equal to 1 over root 8 e to the minus R over 2, 2 minus R. And let me compute one last one. I am erasing this one because this is the computation. All right, let us compute this one. For example, R3, 2. N equals 3, L equals 2. Equals 1 over square root of 3 over 2. N is 3, 3 over 2. L is 2. 2 times 2, 4, plus 3, 7. Times 2n. N is 3, so it is 2 times 3. Then n plus L factorial, so it is 5 factorial. Here it is 3 minus 2 minus 1, so it is 0 factorial. This is 1. This is 5 factorial. So it is 5 factorial, so 5, 4, 3, 2. Times R to the L, that's R square, e to the minus R over 3. L is 12, L 5. N is 3. 3 minus 2 minus 1. So 3 minus 3, that's 0. But this is 1. This is just 1. So let's compute. All we have to do is to compute the normalization coefficient. 3 makes 3 to the 8. Goes out as 3 to the 4. 3 to the square is 9. 9 times 9 is 81. So it is 81 square root. So I have 2 to the 7 So I have 5, 4, 3, 2 times 2 is 4, divided by 2 to the 7. So this is 2 to the 7. I'm just computing the normalization coefficient. So it is 1 over 81 square root of 2 to the 2, 2 to the 4, 2 to the 3. So it is 15 over 2 cubed. Let me multiply by 2, divide by 2. 2 to the 4, square root is 2 to the 2. So it is 4 over 81, square root of 15 times 2 is 30. That's the normalization coefficient. And we are done. R32 is equal to 4 over 81 root 30 r square e to the minus r over 3. So that's the way it goes. So we have the radial functions. We have normalized them. And that's the end of today's lecture. Let me just review shortly what we did. This lecture was composed of 3 parts. In the first part, we obtained the recurrence relations. In the second part, we looked at the Sturm-Liouville theorem and the orthogonality relation of the associated Laguerre polynomials. And in the third part, we looked at the normalization of the actual hydrogen wave function. It did not obey the orthogonality property of the Laguerre polynomial directly. However, with the use of the recurrence relation that is obtained from delta UG, we could take the integral and normalize the wave function with this normalization coefficient. Next, not today, but the next time, the next lecture, we will consider NLM, R to the S, NLM, various powers of S. The interesting powers, well, one of course is the what we did, normalization, and then we have 1 over R, 1 over R square, and R. Okay, these are the simplest. So we shall consider the expectation values of 1 over R square, and R. So that will be the topic of next time. Thank you.